Okay, we'll do some more components. Oh, semiconductors. Uh, that's about all you're going to see in anything modern. Uh, there's still tubes around, vacuum tubes, mostly in like power amplifiers or very high power equipment. In the music industry, musicians like tube amplifiers because they color the sound as opposed to transistor amplifiers, which are, uh, I guess, a much purer sound, but they don't have the distortion, which the musicians seem to like. So that's why you still, when you see the guys with their guitars plugged into that big amplifier there, it's a big amplifier with vacuum tubes in it. Today's semiconductors, for most situations, are going to be made from silicon. A few are germanium, and then there's a couple other materials like gallium arsenide and gallium phosphide, some things like that for special purposes, for high frequency operation or in manufacture of light emitting diodes. They use some of these other materials. But most of your transistors and diodes are going to be made from silicon. And there's basically three types. You have your pure silicon, which we call intrinsic, which has four valence electrons. So it's it's classed as a semiconductor. In its pure state, it's actually pretty much of an insulator. Current will not flow through it without a very strong potential across it. Then we have a P-type and an N-type. And a P-type silicon has a positive net charge to it. N-type obviously has a negative net charge. And we'll talk about a little bit on how those are made. Because in the semiconductor, there's no overlap in those valence and conduction energy bands. They're actually separated. So it takes some amount of energy to free that electron to get it up into the conduction band. And that's where we're going to see this in the case of silicon. It's around 0.7 volts potential in order to have those electrons actually go up and become a free electron and move. In the case of germanium, it's around 0.3 volts. And if we look at our silicon atom with the four electrons in the outer or valence shell, okay, when these are together, it forms a crystal. And we have what we call covalent bonds where these outer electrons share that shell with another atom. So it forms a nice crystalline structure. If we take an impurity, in this case, we take a boron atom, and won't go into the process of how they get there, but they diffuse boron into the silicon. And you can see boron has 3 valence electrons. So it doesn't mate up with the silicon, and you wind up with essentially a hole, which becomes a positive charge because it's deficient of 1 electron for every boron atom in there. The more boron atoms, the the more holes that you're going to have in that material. In the case of making an N-type, we put something like phosphorus. I think arsenic is another one that's similar. It has 5 valence electrons. So when it's embedded in with the silicon, we wind up with an excess electron that isn't shared. So it takes on a negative charge, net charge. So we're going to talk about the first one with the component, which is the diode, where we're going to use 2 of these semiconductor materials. It has 2 electrodes, we call an anode and a cathode. Typically, the physical package for the diode, the cathode end of it will have a stripe, a white stripe, black stripe, depends, to indicate that that's the cathode end. When we apply a voltage to the anode, which we call being forward biased, it will conduct current from the anode to the cathode. If we reverse bias it and put the positive voltage on the cathode, it will not conduct. It acts like an insulator. When it does conduct, depending on whether it's made out of silicon or germanium, we're going to see that threshold voltage that's required to get it to conduct. So if it's silicon, it's going to take 0.7 volts or greater before it will pass current. In the case of germanium, it's going to take 0.3 volts to cross over that threshold and cause it to conduct. When we put these P-type and N-type pieces of silicon together and form this junction between them, what happens is because we have this potential difference, it creates what we call a depletion zone, where the electrons combine with the holes, and we wind up with, in essence, intrinsic silicon in the middle in this depletion zone, which isn't a conductor. And it has this potential difference of the 0.7 or 0.3 volts in order to cause conduction from the P region to the N region. And oops, I can't see this. And this is just showing this potential difference across that depletion layer. This one is, again, showing when we're applying a voltage, a positive or forward biasing voltage, it actually causes that depletion layer to shrink so that we're able to pass current through it once we exceed that potential. What happens is when we reverse that voltage, it causes that depletion region to get much larger, and it becomes more and more of an insulator. So it takes a much, much higher voltage to cause conduction. The symbol that we use for representing a diode is this filled in triangle with a bar. The triangle represents the anode, and the straight line or bar represents the cathode, and that's why we mark the cathode with a stripe, just like on the symbol. This is a plot showing what actually happens. And if we apply a positive voltage, in the real world, there's just some small amount of leakage that you're going to see until you get up to what we call the knee, or that threshold voltage, which is either 0.3 volts or 0.7, depending on whether it's germanium or silicon. And then it starts to conduct. And the slope of that line is going to be determined by the series resistance, some resistance in the diode and whatever's in the circuit. When we do a reverse voltage, okay, even though you still get a small amount of leakage in the opposite direction, you get no significant current flow until you get to the Zener point, where it breaks down and you can have current flow in the negative direction. We take advantage of that in making what we call Zener diodes, where you operate them in reverse potential, and they can manufacture the diode so this Zener or breakdown voltage is very precise. They can make one at 10 volts or 10.2 volts, and we use those as voltage sources, reference sources.
I just have a quick question. So you said you can reverse it, but didn't we just say reverse will not conduct?
Right. If you look at this chart, okay, it will not conduct until you get to the reverse breakdown voltage, which is a much higher voltage.
Thank you.
So in normal operation, it's only going to be conducting in the 0.7 volts and higher potential. This is what a physical one looks like. These tend to be in a glass package. You can actually see the elements inside there, and you see the black stripe marking the cathode end. So this is the anode and this is the cathode, and the symbol in the same direction. This is what the symbol that you're going to see on a schematic for a diode. So what electric component allows current to flow in only one direction?
Charlie.
Charlie. In the water analogy, it's kind of like a flapper valve, where when water is coming through in one direction, the valve opens. When you go in the opposite direction, it forces it to close itself. What are the names for the electrodes in a diode?
Charlie.
How is the cathode lead of a semiconductor diode often marked on the package?
Bravo.
Bravo.
Bravo. What is true about forward voltage drop in a diode?
Alpha.
Alpha.
Alpha. 0.3 in germanium, 0.7 in silicon. And it's actually different values for other types of materials, but we only have to worry about these two for the exam. Okay, light emitting diodes, kind of a special class of diode. It turns out that when you do have conduction or current flow across that PN junction, where you've got electrons that are at a higher energy state in order to be in the conduction band, when they recombine with an atom and go back to the valence energy, they have to give off some energy. It turns out that whether it's a light emitting diode or a regular diode, there's some photons emitted when that happens. And depending on the amount of energy that's released, determines the frequency of those photons. So in a normal regular silicon diode, if it was in a package where you could actually see the element, it would be emitting photons, but probably not in the visible light spectrum. They learned to take advantage of this for making a light emitting diode by using different materials, which determines how much of that, what size that band gap is. So they could get it into the visible light spectrum. So with the right material, you can create a red LED or a green LED or a yellow LED. Later on, they discovered that they could do other things in addition to create blue and white LEDs. So that whenever there's a forward current through the diode, it will emit light in one of those wavelengths. And we tend to use these nowadays for a digital indicator like a power on off, fault indications, because we can use all the different colors and we can turn them on and off, we can blink them. So it's a way of making some type of indicator. Put a bunch of them together in a package where you don't see them much anymore, but the old LED digital readouts where you actually have 7 segments and show, you know, letters and numbers. And this is just showing that recombination process where the energy is released in the form of photons. And that's what creates, depending on the amount of energy, which one of these wavelengths those photons happen to be. It has the same symbol as a regular diode with the exception of a couple little arrows that are meant to indicate the light coming out of it, because it is a light emitting diode. I guess more technically, it's a photon emitting diode. But unless it's in the visible spectrum, you don't see it as light. Usually on the package, and these are made out of some cast plastic, there will be a flat side on it, and one lead will be shorter than the other, indicating the cathode for the short lead, and the anode is the longer lead. There's really no way to put a stripe on it like you would on a regular diode. So what causes a light emitting diode, LED, to emit light?
Alpha.
Alpha.
Forward current. So that means there's enough potential to overcome the threshold voltage and cause it to conduct. And then it, due to the process going on with the atoms, it releases energy in the form of light. Which of the following is commonly used as a visual indicator?
Alpha.
Alpha.
Okay, transistors. So now we're going to take our diode and we're going to add a third piece of silicon. And we're going to use it to control current flow. Where in the diode, the only control we had was the voltage, the forward voltage on it had to be enough to overcome the threshold and then it would conduct. But we can't control directly how much it conducts other than by the voltage. So they came up with the idea to add this third silicon element or germanium so that they could possibly control the current through the device with a external source, a voltage or a current. It turns out they actually tried to do field effect transistors first, but they couldn't make it work. So we wound up with bipolar junction transistors, which they were actually able to fabricate. And we had those for quite a while before the first field effect transistors were practical. And you have two types depending on the layers. You have an NPN or a PNP, which means an NPN is composed of a piece of N-type silicon sandwiched with the P-type. So basically you got a diode, and then you add another N-type to it. So you've got three layers. A PNP is just the opposite. You got P-type, N-type, and P-type, which means your diode junction would be in the opposite direction. For a field effect transistor, which lets you control that current flow with voltage, whereas in the bipolar, it's the amount of input current on the control element that controls the current through the device. We do it with a voltage on the field effect. And again, we have two types. We call an N channel and a P channel. And it's just like on the bipolar. It's three types of silicon, either NPN or PNP. Within the field effect, we're only going to talk about two, junction FETs and metallic oxide FETs. For a bipolar junction transistor, like I said, it's current on the input control element that controls the current through the device or the output. And we have those three regions, P-types with positive charge, N-types with negative charge. And we label those the emitter, the base, and the collector. You see the little diagram over in the bottom right. It shows how those layers are together for an NPN type transistor. And one end is called the emitter. The other type N is the collector, and the material in the middle, which is in this case a P-type, is called the base. And we have two junctions, whereas in the diode we have one. So the base emitter junction kind of behaves just like a diode, where the base collector junction looks like a reverse bias diode. So we don't have current flow in that direction. The symbols that we use, it will come up later on the schematic diagram, showing the three electrodes, emitter, base, and collector. And we show the base as this middle section. This kind of indicates the actual substrate this thing is built on. And we have the other two N-type materials. So the base emitter, okay, is our equivalent to our diode. And that's why it looks kind of like a diode between the base and the emitter. Just a straight line out to the collector. In the case of the PNP, we just reverse the direction of the current flow. So in the NPN, when I apply a current on the base, and it goes from the base to the emitter, I can control the amount of current that flows between the collector and emitter. In the case of the PNP, current coming out of the base from the emitter, I should turn email off, will control current flow from the emitter to collector. this is kind of a cross section of what a typical junction transistor looks like when it's fabricated. So we have a block of N-type material, and get embedded in that, they fabricate some P-type material, and then a smaller piece of N-type material, which becomes the emitter. This P-type in between is the base, and the rest of that piece of silicon, N-type, is the collector. And you see the collector is much, much larger than the other two elements. And the way it works is you apply a voltage which causes a current flow through the PN junction, and through a process I'm not going to go into a lot, can actually cause a much larger current flow between the collector and emitter. And the amount of gain, or what we call beta, of the collector to emitter current versus the base emitter current is going to be proportional to the thickness of this P layer. So the smaller that is, the larger amount of current we can control from the current emitter with the base emitter current. This
I just
kind
have
of
a quick question. Sorry to interrupt here.
Sure.
Do transistors use gates? I thought there was a gate somewhere on the base. Is that familiar with transistors?
Yeah, but we haven't got to field effect transistors yet.
Oh, okay. Okay, you're coming up to. Thank you.
Bipolar junction have emitter, base, and collector. Field effect transistors have source, drain, and gate. So we'll get to a gate shortly.
Oh, gotcha. That's where I was getting confused. Okay, thank you.
Okay. So in this, we're showing what we call the bias voltage between the base and emitter, and the supply voltage between the collector and emitter. And that's what it would look like in actual schematic. And that current between the base and emitter will cause a much larger current flow from collector to emitter once you get over that threshold, just like in the diode. If this is a silicon transistor, it's going to require 0.7 volts or higher potential difference for that to create or conduct current from base to emitter, and therefore conduct current from collector to emitter. The process of that input current versus output current, they call transconductance. So you can have a very small signal coming into the device on the base, and we see a much larger signal due to the current through the device. And that amplification is dependent on the slope of this line, which is again proportional to the thickness of that PN layer. And you don't really need to know all this stuff, but it's just there. Which of the following components can consist of 3 regions of semiconductor material?
Bravo.
Bravo.
What are the names of the electrodes of a bipolar junction transistor?
Bravo.
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 Field effect transistors. In this case, we're going to use a voltage to control the current output by way of using an electric field, which is why it's called a field effect transistor. It still has 3 semiconductor regions, and we call those the gate, the drain, and the source. You can have 2 types, whether it's called P channel or N channel, very similar to the bipolar junction. The symbols that we use, in this case, it's a junction field effect. We have the gate and a drain and a source. And you notice these look fairly symmetrical. Actually, they are. In the case of this field effect transistor, we can reverse the drain and the source. It doesn't really matter how you hook them up because they're both, the way it's built, it's symmetrical inside, and it's this channel in between them that controls the amount of current flow, which is controlled by the electric field created by the gate. If we have a P channel type, we just show the gate symbol showing current flow or voltage in the opposite direction. Physically, this kind of a cross-section of what a junction field effect transistor would look like, where we have the basic N-type material and then some P-type on either side of it. And the center section, which is the gate, which actually is connected internally, or maybe, when we put a potential across the, here's the gate. Across the gate, that electric field opposes the flow of current through this N-type material. And so it's proportional, and it works just like applying a current on the junction transistor. As we apply a voltage and we increase or decrease the field between these two pieces of silicon, it will control the amount of current that can actually flow through what we call this channel. There's just some more figures of kind of implementations, but you notice it's basically a symmetrical type of device. This is just a plot of the current through the device, depending on the voltage on the gate, between the gate and the source. And it shows that in this particular case, if there's 0 voltage on the gate, okay, it allows the maximum current to flow. As we apply a negative voltage on the gate, and this is an N channel, it kind of pinches off the current flow with that field. And we get all the way down to, in this case, around -4 volts. We get to what we call pinch off, where basically there's no current allowed to flow. Whereas if there's no voltage on the gate, in this case, the maximum amount of current, or the saturation region. And that's how we also use it as a switch, by applying either 0 volts, or in this case, -4 volts or greater. It'll either turn it on or turn it off like a switch. If we wanted to use it as an amplifier, we would set a bias voltage, say -2 volts, and apply an input signal, which would vary around that bias voltage and control the amount of current through the device. It's just another kind of cross section, except this is what we call a metallic oxide, I forget what the S stands for. Surface? Anyway, the way they make these is a P-channel body, a couple pieces of doped N-type on the ends, and this is a metal element, and there's a metal oxide which acts like a dielectric. So it's kind of like making a capacitor. We've got an electric field between the gate and the body. So it kind of pinches off the current flow, in this case, through the this channel between the drain and the source, and proportional to the voltage or that field controls the amount of current that can flow through it.
S is semiconductor.
Hmm?
S is semiconductor. Metal oxide
Semiconductor.
You'll get that transistor.
So what does the abbreviation FET stand for?
Delta.
Delta.
Very good. What type of transistor has a gate, drain, and source?
Bravo.
Bravo.
Okay. Applications of transistors. Like I said, we can use them as switches where we apply a voltage or a current that either puts it into saturation or cut off, or in the case of FET, pinch off. So there's either the maximum amount of current flow or no current flow. If we use it as an amplifier, then we bias that input or control voltage or current somewhere in the middle of the range to make it as linear as we can get it. And the signal on that control element will control the current through the device proportional to it based on the gain of the device, or the beta, which again is proportional to, in the case of the junction transistor, how thick that layer is. So the thinner you make it, the higher the gain, but then also the lower voltage that it can operate at, because at some point you would break over that region. And we call that ratio of output to input gain. And usually we do it as a logarithmic function. So we'll take the log of the output versus the input ratio, and we'll define that as the amount of gain in decibels for the device. Oh, this chart should have been moved up, showing a similar thing for a bipolar junction, where these curves are various amounts of base current, base emitter current. And the bottom is going to be the amount of collector emitter voltage we see versus the collector current. And in the case of a switch, we're either going to bias it so we're operating down here when it's turned off, or up here where it's in full saturation. In the case of using it as an amplifier, we'd probably set it up so it was biased with whatever this base current is and let it operate in this region. Which of these components can be used as an electronic switch?
Charlie.
Charlie sounds good. What is the term that describes a device's ability to amplify a signal?
Alpha.
Is it up? Oh, gain.
All right, gain. The ratio of the output to the input. Which of the following can provide power gain?
Bravo.
Bravo.
Bravo. Yeah, actually, you can have power gain, voltage gain, or current gain, depending on the way you configure the device. Okay, so we learned that diodes conduct current in one direction. The forward bias for germanium is 0.3 volts, for silicon is 0.7 volts. We mark the cathode of a diode with a stripe. A light emitting diode emits light when it's forward biased. Transistors can have power gain, can be used as a switch or an amplifier. A bipolar junction transistor has base collector and emitter electrodes, and a field effect transistor has gate, drain, and source electrodes.